Hi, welcome back to my channel. My name is Gina. In this video, we are going to talk about the simple harmonic motion. Simple harmonic motion is seen everywhere in our life. A child on a swing, a string on a guitar, and even the sound wave. The fact that you can hear me is because the air molecules are oscillating in simple harmonic motion. So what is a simple harmonic motion? It is an oscillatory motion with linear restoring force. So we can write the linear restoring force as negative some constant times x. The x here has exponent of 1, that is why we call it the linear restoring force. And why the negative? Because the restoring force will always try to bring the object back to its equilibrium point. So if we set the equilibrium point as x equals to 0, if an object is in the positive x region, then the restoring force will be pointing in the negative direction because the force will try to bring the object back to its equilibrium point. And if the object is in the negative direction, then the restoring force will now pointing in the positive direction. In this formula, the x is the displacement away from the equilibrium, and k is some positive constant. Now let's find the equation of motion. From Newton's second law, we know that net force, and let's focus on the x component only, it equals to mass times acceleration in x. Then we can isolate for the acceleration. So acceleration is sum of F, or net force, divided by the mass. And if the restoring force is the only force acting on the object, then acceleration is negative kx over m. We also know from mechanics that acceleration is the second derivative of x, the displacement. So we can write equation of motion as second derivative of x equals to negative k over m times x. And that is our equation of motion. And note that this equation of motion is a differential equation. It involves the second derivative and the x. Now let's try to find the solution to the simple harmonic motion, which is we want to find x as a function of time that satisfies the differential equation that we just found. And let's have a trial solution. In physics, trial solution, we often call it the ansatz. Let's try a cosine function, because when you watch a child on a swing, or when a mass is attached to a spring and is oscillating, you'll see the pattern of displacement as shown in the plot. So we can kind of guess that the solution may be something related to cosine function. So let's use ansatz. Let's try x as a function of time is some constant times cosine of omega times t plus some other constant, phi naught. Here the omega is angular frequency. Its unit is radians per second. And phi naught is the phase constant. Its unit is in radians. So to verify that this is a solution to the differential equation, we need to calculate the left-hand side and right-hand side separately. And if this is a solution, then the left-hand side should equal to the right-hand side. Let's start with the left-hand side, which is the second derivative of the displacement. We have the trial solution is x equals to a times cosine of omega times t plus phi naught. Its derivative would be negative omega times A times sine of omega times t plus phi naught. And its second derivative, which is derivative of the first derivative, it would be negative omega squared, because we use the chain rule. The inner function is omega times t plus phi naught, so its derivative is omega. Then times derivative of sine is cosine. So cosine of omega t plus phi naught. Now let's compute the right-hand side. Right-hand side is negative k over n times x. We substitute the trial solution, the x, into the right-hand side. We get negative k over n times a times cosine of omega t plus phi naught. Now let's try to equate the left-hand side with the right-hand side. Left-hand side, it was negative omega squared times a times cosine of omega t plus phi naught. And right-hand side, we have negative k over n times a times cosine of omega t plus phi naught. We can cancel out the a times cosine function on both sides. And we have negative on both sides, so we can cancel out the negative sign. So we are left with omega squared equals to k over n. Omega squared, since we have the square, so left-hand side is always positive. How about the right-hand side? K, we say that is a positive constant, so yes, it's positive, and n is the mass, which is always positive. So we just verified that our trial solution is the solution to the simple harmonic motion, with omega equals to square root of k over n. So just a quick summary of how we derived in the last slide. We found that if the equation of motion is in the form of second derivative equals to negative omega squared times x, where omega squared is positive, then the solution is a times cosine of omega t plus phi naught. Note that we can also write the solution x of t as a sine function. Since sine and cosine, they are basically the same function, but with a phase of pi over 2. Because cosine of theta is the same thing as sine of theta plus pi over 2. Another important quantity in simple harmonic motion is the period, which is the time for one oscillation. And one oscillation is when the phase changes by 2 pi. And the phase is the thing inside the cosine function. So omega of some t naught, plus the period, which is time for one oscillation, plus phi naught minus omega times t naught plus phi naught. So if the phase change is 2 pi, the delta t should be 1 period. The first term can cancel out with the first term of the second phase, and phi naught can also be cancelled out with the phi naught. So we are left with omega times the period equals to 2 pi. And we get period is 2 pi over omega. And frequency would be number of oscillations per unit time, which is the same thing as 1 over period. And we just found that the period is 2 pi over omega, so 1 over period is omega over 2 pi. So here we get omega is the same thing as 2 pi times the frequency. And that is the end of the introduction to simple harmonic motion. Next week, we'll look at 3 examples on simple harmonic motion. If you like my videos, please like and subscribe, and I'll see you next week.